All right, welcome to M47, which is photochemical smog and acid rain.
1943. Los Angeles was blanketed by a thick gas that stung people's eyes and blocked out the sun. Panicked residents believed their city had been attacked using chemical warfare. But the cloud wasn't an act of war. It was smog. A portmanteau of smoke and fog, the word smog was coined at the beginning of the 20th century to describe the thick gray haze that covered cities such as London, Glasgow, and Edinburgh. This industrial smog was known to form when smoke from coal-burning home stoves and factories combined with moisture in the air. But the smog behind the LA panic was different. It was yellowish with a chemical odor. Since the city didn't burn much coal, its cause would remain a mystery until a chemist named Ari Hagenschmidt identified two culprits: volatile organic compounds, or VOCs, and nitrogen oxides. VOCs are compounds that easily become vapors and may contain elements such as carbon, oxygen, hydrogen, chlorine, and sulfur. Some are naturally produced by plants and animals, but others come from man-made sources like solvents, paints, glues, and petroleum. Meanwhile, the incomplete combustion of gas in motor vehicles releases nitrogen oxide. That's what gives this type of smog its yellowish color. VOCs and nitrogen oxide react with sunlight to produce secondary pollutants called PANs and trophospheric, or ground-level ozone. PANs and ozone cause eye irritation and damage lung tissue. Both are key ingredients in photochemical smog, which is what had been plaguing LA. So why does smog affect some cities but not others? Both industrial and photochemical smog combine man-made pollution with local weather and geography. London's high humidity made it a prime location for industrial smog. Photochemical smog is strongest in urban areas with calm winds and dry, warm, sunny weather. The ultraviolet radiation from sunlight provides the energy necessary to break down molecules that contribute to smog formation. Cities surrounded by mountains, like LA, or lying in a basin, like Beijing, are also especially vulnerable to smog, since there's nowhere for it to dissipate. That's also partially due to a phenomenon known as temperature inversion, where instead of warm air continuously rising upward, a pollution-filled layer of air remains trapped near the Earth's surface by a slightly warmer layer above. Smog isn't just an aesthetic eyesore. Both forms of smog irritate the eyes, nose, and throat, exacerbate conditions like asthma and emphysema, and increase the risk of respiratory infections like bronchitis. Smog can be especially harmful to young children and older people, and exposure in pregnant women has been linked to low birth weight and potential birth defects. Secondary pollutants found in photochemical smog can damage and weaken crops and decrease yield, making them more susceptible to insects. Yet for decades, smog was seen as the inevitable price of civilization. Londoners had become accustomed to the notorious pea soup fog swirling over their streets until 1952, when the Great Smog of London shut down all transportation in the city for days and caused more than 4,000 respiratory deaths. As a result, the Clean Air Act of 1956 banned burning coal in certain areas of the city, leading to a massive reduction in smog. Similarly, regulations on vehicle emissions and gas content in the U.S. reduced the volatile compounds in the air and smog levels along with them. Smog remains a major problem around the world. Countries like China and Poland that depend on coal for energy experience high levels of industrial smog. Photochemical smog and airborne particles from vehicle emissions affect many rapidly developing cities, from Mexico City and Santiago to New Delhi and Tehran. Governments have tried many methods to tackle it, such as banning cars from driving for days at a time. As more than half of the world's population crowds into cities, considering a shift to mass transit and away from fossil fuels may allow us to breathe easier.
All right, so this is from your book, and this is how natural ozone forms. So this is important, an important equation. So make sure you understand it. So basically, the top is just showing the chemical formula, the structure, and then this is the equation, and then description of what's happening. So the equation is what's important in understanding it, not necessarily the structural formula. But the chemical equation, we've got nitrous oxide plus nitrogen oxide plus oxygen, and that forms O3 eventually, and O3 is ozone. So it just explains here nitrous oxide forms when there is an abundance of Vox, Vox are scarce, and then there's abundance of nitrous oxide. And then you've got nitrous oxide splitting to form free oxygen. So basically, nitrous dioxide forms nitrous oxide plus oxygen by itself. And then now you've got oxygen, O2, which is what we breathe, combining with that free radical oxygen, and that forms ozone. And so this is constantly forming and breaking up, like constantly. That is normal. But when we have an excess of nitrous oxide on the surface of the Earth, then that creates ozone on the surface. And so we don't want that. Ozone up in the stratosphere is great because it blocks the UV radiation, but O3 on the surface is what we call smog. And so we do not want that. And then here on the next slide, it shows destruction. So like I said, this is constantly happening. So O3 is constantly forming and breaking up. So you've got O3 plus nitrous oxide, and basically that free oxygen disconnects and forms O2, which is what we breathe, plus nitrous oxide. So it's a constant back and forth. And this is in the presence of sunlight. And then, the last equation is in the presence of sunlight. And then without sunlight, it breaks down. So you can see during the daytime, O3 would be forming, and at nighttime, it's breaking apart. And that's because of sunlight. All right, so the health effects of smog. So we've got the smog forming on the surface for a variety of reasons, burning of fossil fuels, combustion, things like that. So factors that contribute to smog, VOx, NOx, so that acronym again there, sunlight, PANS, which stands for I can't pronounce it, but peroxyl nitrates formed from hydrocarbon and oxygen. And so basically just know them as PANs, but they are forming from hydrocarbons, which are something that forms when we burn fossil fuels. And then ground level ozone, so that's O3 on the ground, and then urban areas surrounded by mountains. So think of like Reading, for example. So sometimes we have really high pollutant levels, but we don't have a lot of pollutants being put in the atmosphere. We're not Sacramento. We don't have a large city, but we're surrounded by mountains. And so what happens is the delta breeze brings up that pollution. And then because we're surrounded by mountains, it stops. And so we do get some high pollution days, even though we we're not really contributing to a lot of pollutants in the atmosphere. But we get that because it comes up through the delta. So health effects of smog, eye, nose, throat irritation, lung damage, respiratory infection, asthma, low birth weights, and birth defects. All right, acid rain. So acid rain is formed from SO2 and NOx. So just think of SOx and NOx for acid rain. So that combines with the oxygen, the O2 that we're breathing, and that forms secondary pollutants like we talked about. So the secondary pollutants the effect would be acid rain. So the primary pollutants, SO2 and NOx, by themselves, they're not producing acid rain, but combining with oxygen, and then they're forming sulfuric acid and nitric acid, and then that's precipitating down. So that's why it's a secondary pollutant, because it has to combine with oxygen first. And so the effects of acid rain, agriculture can be hurt because you've got something more acidic raining down on it now. So the crops aren't going to grow as well. The ground is going to be too acidic. It's not going to be neutral enough. And then also, so we get trees dying. So just forests dying. Amphibians and things like I mentioned before, they can't reproduce very well. They're eggs dissolve in the acidic water. We don't feel the effects of acid rain though, so the acid rain is way less acidic than soda. So if you're to pour soda on your arm, you're not going to feel that. But so you're not going to feel acid rain. But to organisms that are sensitive to it, it's a big deal. It's like, you can't water your plants with soda. That's not going to work out. Whoops. So it says down here, the last bullet tends to be worse in the east because of the jet stream. So the jet stream blows from the west to the east. So it's carrying all of the pollutants with it to the east. So we tend to see acid rain affect the east coast way more than it does the west coast. And that's because all those pollutants are blown across the US towards the east. All right, so other systems that can be affected, like I mentioned, organisms can't tolerate low pH, so they tend to not do well in streams and lakes. Forests, they tend to, not do very well when they're watered with acid water. And then just destruction of human stuff. So you can see some pictures here. The one on the left is a forest that's been killed by acid rain. The middle picture, if you've ever been to a really old cemetery, they have gravestones that are very, very hard to read. And that's because they were made with marble. And marble is the metamorphic version of limestone. And limestone dissolves in acidic things. So remember when we talked about ocean acidification and shells are dissolving? So this marble is basically like a metamorphosized shell. And so it's affected by acid rain. And so if you go to read like the gravestone, you can't read it very well. It's like really kind of light and almost like the words are disappearing. And that's because they're dissolving. And that's because it's made of marble. And so we don't generally make gravestones out of marble anymore. We make them out of granite because granite does not dissolve because it's not made of calcium carbonate. And so it won't dissolve like marble did. And then on the right, of course, fish are affected by acid rain. They can't tolerate low pH levels either. And that's it. So hopefully you enjoyed, and I'll see you next time.